All right, this is the last segment for this unit, and it goes back to 1904. It was in the climate change chapter. We took it out because we felt it went better with air pollution, which it does and should be here anyway. So, the ozone layer. We already know that the good ozone layer is in what layer of the atmosphere? Good. The stratosphere. I almost said troposphere. Stratosphere. Very good. So, ozone is made up of 3 oxygen atoms, so it's O3, a very unstable molecule. It doesn't like to exist like that. Oxygen prefers being O2, but when oxygen reacts with ultraviolet light in the stratosphere, it forms O3, which is good because it's a protective blanket that absorbs a lot of the UV light that would otherwise damage living tissues. Before photosynthetic organisms, right, there's no chance of life getting any more complex because there was no oxygen to create this ozone to then protect us from the UV light. So it was the photosynthetic organisms that produced oxygen gas as a byproduct of photosynthesis that allowed there to be oxygen, which allowed there to be this reaction and this protective blanket. So in the stratosphere, it's great, protects us from cancer, from cataracts by filtering out 95% of the harmful UV rays. However, remember that ozone in the troposphere is a pollutant, it's bad. So, I'm trying to remember the saying how it goes now. Ozone up high, good ozone up high, bad nearby, I don't remember. But in the troposphere, it's bad, you don't want it. You don't want it. This is just showing you that we've got there's different types of UV radiation. A, B, and C. A has the highest intensity, right? So it can make it through, and that's the ozone or the UV light that we do get is UVA. But UVB and C are predominantly filtered out. Ozone, this is bent polar molecule, 3 oxygen molecules bound together. Lovely. Alright, so this is a picture of the ozone hole. And like I said in one of the other slides, or one of the other presentations, it's a misnomer to say a hole. It's more of a thin spot, like the thin spot on the heel of your sock. You can see your skin through it, but there's still some threads holding it together. It's that type of thin spot. And it occurs at the poles. And I'll explain that in just a few. So this was before we started getting that hole, there's a thin spot in the ozone layer, and this was in the 90s, where it's very evident that it's present. So CFCs are the culprit. Those are chlorofluorinated carbons. Let's see here. They were invented in the 1920s to be a refrigerant. They used them to make different types of styrophones, right? So they're, again, industrial application. Nobody thought anything about it. We used them as a propellant in aerosol cans, widely used. And in 1985, a British scientist announced that there was a thin spot in the ozone layer above Antarctica. Like, wow, what's going on? What's happening? So they traced it back to the CFCs. Here it says, because of atmospheric conditions, the CFCs build up over Antarctica during the winter. And this is true. So CFCs will break apart ozone. At the poles, because of the Earth spinning, we get kind of like these vortexes that occur at the poles. And the CFCs, they get sucked into them, right, when the north is tilted away from the sun, right, that's when it's in winter. So during the winter months, those CFCs become inert, right, they're not functioning. Then as the spring comes around, all those CFCs that were frozen, right, now they start to unthaw and they become reactive. So all of a sudden there's all these CFCs that have been sucked into these vortexes throughout winter, so there's an overabundance in them, and then once they unfreeze, right, then they start going crazy and they just destroy the ozone locked in that pole, right? So the thin spot goes back and forth during between the North Pole and the South Pole, right? So during the spring of the North Pole, right, where the ozone is being depleted, it's being replenished at the South Pole, and then they'll flip-flop back and forth based on season. So the chlorine destroys the oxygen, and it strips away oxygen from the ozone molecule. I'll talk about that next slide. 1987, the Montreal Protocol started banning these chlorofluorinated carbons. Developed countries had to stop using the most harmful ones by 1995. Developing countries were giving a reprieve of 15 years. They just stopped using the most harmful ones by 2010, so that was 5 years ago. When I say most harmful ones, we still use some CFCs, but they are the least harmful categories. And eventually those will also be phased out, but that timetable has not yet been set. So the hole is beginning to shrink, but the problem is these CFCs can take anywhere from 10 to 100 years to float into the stratosphere. So with that being said, some of the CFCs that were released in the 1920s and 30s could still be ascending into the stratosphere. So it's going to take a long time, about another 50 years before it's kind of replenished. So when 2080, it should be back to 1950 levels, meaning the amount of ozone in the stratosphere. So what's going on? The CFCs, again, it takes 10 to 100 years to float to the stratosphere. The UV light, first off, rips off one of the chlorine atoms on these CFCs, and that one chlorine atom can then go through and destroy 10,000 ozone molecules. Right? It will attach itself to one of the oxygen molecules, rip it off, then the UV light splits that chlorine from the oxygen, and then that chlorine is now free to rip off another oxygen from a new ozone molecule, and it can do this up to 10,000 times before it falls back to Earth. So we have released more than 12 billion pounds of CFCs into the atmosphere since the 1920s. So there's an abundance up there to wreak havoc on the stratosphere, and it has done so. So CFCs were banned, even though CFCs were phased out starting in 1987. The damage will continue for decades. It takes a long time for these things to stop destroying the ozone molecules, and some are still, like I said, ascending up into the atmosphere. But you can see CFC concentrations. It doesn't exist naturally. It's an industrial chemical, so there's none here, none here, none here until we get into 1950s, where air conditioners really became a thing, which is what made living in Florida a possibility. It didn't happen until air conditioners. So once that happened and air conditioning became prevalent in everyone's homes, you can see the quantity of CFCs skyrocketed. So the Montreal Protocol is what put the end to that, and it's one of those few things that we have done as a worldwide organization. We've gotten together and we said, all right, we're going to stop using this substance, and everybody agreed to it. Everyone stuck to it, and we're actually noticing an improvement in the ozone layer. Right? So a lot of times on FRQs, if they'll ask you to discuss something that we've done that's been beneficial to the environment as an international community, this is pretty much one of the few things that you can cite. The Montreal Protocol, which has been effective in decreasing the quantity of CFCs in the stratosphere, and has improved the ozone layer. So yeah, there we go. We're making a difference. It's beautiful.